Chapter 9. In Chapter 9, we will be looking at free or natural convection, and we'll be looking at how to derive some dimensionless groups and how to solve uh, heat transfer problems when you have natural convection uh, through a surface, or if you have a temperature difference, how will you calculate the heat transfer rate in that scenario. So we've already briefly defined what natural convection was or free convection was. So it's nothing but flow which is driven by density difference. So it's a density driven flow. You need to have density gradients which are caused by temperature differences. So uh, we know that density is a function of temperature, and as temperature changes, you might have seen this in thermodynamics. So as temperature changes, your density of the fluid will change, and due to buoyancy, if you have uh, if you have density differences, you will have a current cause, or you'll have a motion of fluid due to either buoyancy or due to the gradient itself. So this flow can be caused due to a body force like gravity. So you may have buoyancy under the influence of gravity, or you may have flow under the influence of gravity, and you always have a buoyancy in the vertical direction. So it's in the opposite direction of the gravity. So in fluid mechanics, or let's go back to fluid mechanics once. Let's say you have a vertical plate, and you have gravity in the downward direction as shown here. You don't have any uh, flow flowing across the plate. So there are ambient conditions, and there's no flow um, at there's no free stream flow flowing across the plate or over the plate. So how will your velocity profile look like inside the boundary layer? So inside the boundary layer, your velocity profile will look something like this if you have a hot plate. Now what I mean by that is, say this plate here, it's the same plate here, it's hot. That means your T that means Ts is greater than T infinity. You will have a boundary layer which will have an increasing flow rate inside the boundary, and gradually it will decrease and go back to zero because you don't have any free stream velocity, and your temperature distribution will still look almost the same. So your surface temperature will be at Ts, and as you move towards the boundary layer, your temperature near at the boundary layer will be almost equal to the free stream temperature. So your boundary conditions can be defined as y is equal to 0, u is equal to 0, which is the no slip boundary condition, and you have temperature equal to Ts there. At y is equal to infinity, you have u equals to u infinity, but your u infinity is 0, and your temperature is T infinity. So these will be your boundary conditions. Now what happens is that, let's say you have a solid piece of something, a ball or something, and let's say that initially this ball or this particular source, let's say it's a source term, let's say this particular piece of source is at the same temperature as the surrounding. Okay, so now let's assume that magically it starts getting hotter. So as it starts getting hotter, it will heat up the air around it. Okay, and the heated air will rise up. Okay, and this will actually create an upward motion of fluid around it, and that upward motion will be due to a temperature gradient. Okay, so this is what it means when I say that there's a current produced due to buoyancy. So moving on to some mathematics, let's define a few equations. So uh, we can define our fluid in a particular domain by a set of equations which are called the Navier-Stokes equations. So the Navier-Stokes equations comprise of a conservation. They are conservation equations. So you'll have a conservation of continuity, which is nothing but a differential form of conservation of mass. Okay, so conservation of a continuity equation is nothing but conservation of mass. The second is conservation of momentum. So conservation of momentum is nothing but uh, Newton's law, which says that force is equal to mass into acceleration. So or the change in momentum is equal to the mass into acceleration. Change in momentum creates acceleration. That is nothing but the conservation of momentum that we'll be looking at. And third is the conservation of energy. Okay, so in this particular slide we will be focusing on a fancy looking version of conservation of momentum, or a fancy looking version of uh, Newton's law. So it looks something like this, where you have u times per del u by del x plus v times del u by del y. And again, remember, u is the velocity in the x direction, v is the velocity in the y direction. Okay, so on the left you have on the left hand side you have u del u by del x plus v del u by del y equals to the gradient of pressure with respect to x in the x direction, obviously, and it's per unit mass because it's divided by the density. The whole uh, equation is per unit mass plus viscosity times del square u by del y square, and this term here looks similar. It's the shear stress, or it's the viscous effect, times the gravity itself. Okay, so the term on the left here is nothing but the local acceleration of a fluid element. So if you are looking at a control volume or a small element of fluid, the local acceleration of that fluid will be the term on the left. Now you have our acceleration. So on the right will be your the change in momentum or the forces. So because it's per unit mass, the first term is the forces due to pressure difference. Second term is the forces due to viscous interaction, and the third term is forces due to gravity. Okay, so you just need to know what these equations or what these terms mean, as in what do you mean. So what the you just need to know that the terms on the left are accelerations and something like that. So let's say that this is equation 1. So we know that at free stream, outside the boundary condition or far away from the surface, we have u equals to 0 if we have natural convection. Obviously we are doing this for free convection, so our u will be equal to 0. There will be no uh, flow, there won't be any flow of fluid there. So let's substitute this in equation 1. So if you substitute u is equal to 0, your first term will be 0. If you differentiate u equals to 0 with anything, your del u by del y will also be 0. So you have 0 on the left hand side. On the right hand side, you will have this term. Your second term or your viscous term will be 0, and you'll have the gravity term. So eventually, this is what you'll get. You'll get 0 equals to minus 1 by rho. that's the density of fluid, times the pressure variation with respect to x minus gravity, and we can write this as del p infinity by del x equals to minus rho infinity into g. Okay, so now let's take this definition of uh, let's take this definition of rho p by rho del p by del x and substitute it right here. Okay, so the equation that we'll get will be our left hand side. The first two terms will be same. The only term that will change is this term right here. So we substitute minus rho infinity times g, and we have a rho in the denominator as well, and we also have a g which was originally there in the equation. Okay, so I can write this equation. I can take g in common and write the terms as del rho by del. Now del rho here is the difference in the density. So density at that particular location or within the boundary layer, and tin rho infinity is the density of the free stream plus the viscous term. Okay, so why are we doing this? We are doing this so that we get a dimensionless group which will help us to define a uh, which will help us to define or characterize the type of flow. That's if the flow is laminar or turbulent. So our aim here is to find a dimensionless group. So this term here is called the buoyancy. It's the buoyancy per unit area. So you have your change in density times the gravity per divided by rho. So you have your buoyancy per unit area. Now the del rho here is only due to temperature variations. Now this is a very important statement. So what this statement says is that the density difference that you consider in free convection is only due to temperature difference and not due to pressure difference. Now what that means is that your flow will still be incompressible. So your flow is incompressible. You just have the change in density due to temperature and no change in density due to pressure. Okay, so keep that in mind. So what we do is that because our density is just due to temperature variation, we can use the definition of volumetric thermal expansion, which is a thermodynamic property, and it is defined as beta is equals to 1 by minus 1 by rho times the variation of rho by with respect to temperature at constant pressure. Okay, this P here means constant pressure. So if I have to write an approximate form of this, I would write it as minus 1 by rho times del rho by del T, which is nothing but minus 1 by rho times rho infinity minus rho, which we've defined here, divided by delta T can be written as T infinity minus T. Now this approximation here is called the Boursiness approximation or the Boursiness approximation, and it states that your change in density is proportional to the change in temperature times the thermal expansion coefficient times a reference density. Now, what will these rho's and t's be? So that's where the film temperature comes into picture. So if you're asked to calculate the thermal expansion coefficient, you will assume you will find the film temperature at that particular for that particular set of temperatures. So you'll be given a surface temperature and a free stream temperature, and your film temperature will be the average of these two temperatures, and your thermal coefficient will be the value of that film temperature. So after we replace this particular equation here, we get this equation. So the equation we get is, our left hand side is the same. Our first term on the right is g times beta times T minus T infinity plus the viscous term. Okay, so now we have changed the form of our x momentum equation that we originally had, but we still don't have a dimensionless form of this equation. So our next step would be to uh, translate this equation right here into a non-dimensional form. That means we'll have to use some normalized variables. So to find the non-dimensional numbers, what we'll do is that we'll use the momentum equation, the modified momentum equation that we just calculated, and we'll substitute and we'll normalize our variables in the equation. So what does normalize mean? That we will normalize each variable. So our new variable will be called x star and y star. We'll normalize x by L. So x is in meters, L is in meters, and L can be whatever characteristic length you have. So if it's a plate, it will be the length of the plate, for example. So your x will be in meters, your L will be in meters, so your x star will be uh, just a non-dimensional or dimensionless quantity. Similarly, we'll uh, normalize y with respect to L, and you'll get y star as a dimensionless quantity. And we can write this, and we can write x as x star into L, y as y star into L. We can write u in u star. We can normalize u star uh, as u divided by u infinity, because these are the values that we know. So we know what L is, we know what u infinity is, and similarly we'll do the same thing for v star. We'll normalize it by u star again, and in this case we can write u as u star into u infinity, v as v star into u infinity. And for temperature, we'll use a slightly different approach. So we'll take a temperature difference and then normalize it by a known temperature difference. So our temperature will be T minus T infinity divided by surface temperature minus the temperature at infinity. Okay. Now, if we have to find so what will our del T by del Y be? Okay. So our del T by del Y will be nothing but T minus Ts. So we take this on the left hand side, T S minus T infinity times del T star by del Y. Our del U by del X will be, so we'll substitute in del U by del X, we'll substitute U by U star into U infinity, and X, we'll substitute X by X star into L. So our del U by del X will be U infinity by L into del U star by del X star. And similarly, if we have to find U, if you have to find U into del U by del X, you'll just multiply U to the previous equation, which will give you U star U infinity square by L times U star into del U star by del X star. And similarly, you can do the same thing for your second term on the left hand side. That's V times del U by del Y, and that will give you del square times u star u infinity by del times y star by L square. Okay, so we have defined our terms in the x momentum equation in terms of normalized variables. So let's substitute them in the equation that we have. So on substituting, our first term here is this term on the this term here. So let me just, so this is our first term here. Similarly for the second term, it's our this term right here. I just substituted the definition of t minus t infinity. So our t minus t infinity is nothing but t star times ts minus t infinity, and our last term, which is the viscous term, is what we calculate. Oh, so this term is not here. This term is something that we found here. Okay, so our this equation simplifies to uh, this right here. So what I've done is I've multiplied the entire equation by Ly u infinity square. So this term here gets cancelled out after you multiply it by L times u infinity square. So you just have u star times del u star by del x square, del x star plus v star times del u star by del y star equals to g times beta times L times T star times the temperature difference by u infinity plus a plus viscosity by u infinity times L, and this thing here looks familiar, times the normalized viscous term. So this thing here is nothing but 1 divided by Re, where the Reynolds number is defined as U times L by viscosity. So what we do is that we need a non-dimensionless, or we need a dimensionless number, right? And it would be great to have the coefficient of T star as 1. So what do we need for that? So let's say our u square or u infinity square is equal to the quantity in the numerator. So let's say the value of u infinity square is g beta times ts minus t infinity times L. Okay, and let's define a variable. Uh, let's define a dimensionless group called GR, which is the Grashof's number, and let's say it's equal to the square of Reynolds number. Okay, so this will give us, and I'm substituting the definition of u infinity square here. So on substituting that, we get our Grashof's number equal to g times beta times ts minus t infinity multiplied by the cube of length square divided by the viscosity square. So this is the definition of the Grashof's number, and this is a very important definition. You must know you must know the definition of it. You need not know how we have calculated it, so you need not focus on the derivation. You should just know how we derived it, but you don't have to memorize it. And the Grashof's number here, as we said, is the ratio of the force due to buoyancy divided by the viscous forces, and this helps us in defining the characteristic of the flow. Okay, so moving on, we so far we have looked at two types of numbers, which in a way we can say are sort of analogous, which create an analogy between fluids and heat transfer. So the first is the Reynolds number, which is the ratio of inertia to viscous forces, and second is the Grashof's number, which we just derived. And there is another number called the Nusselt number, and the Nusselt number can also be defined as the Grashof's number, or the Grashof's number divided by the square of Reynolds number. So this here is also a very important definition. And why? Because this characterizes what type of convection we have. Okay, so if the ratio of Grashoff's number, or if your Nusselt number is a very small value, very smaller than 1, that means that your free convection effects can be neglected. What that means? That you will have forced convection, right? But if it's the other way around, and if your Grashoff's number, the ratio of Grashoff's number to the Reynolds number square is a very huge number, what that means? That means that your denominator is dominating. And what's your denominator? Your denominator has buoyancy forces. So that means your buoyancy forces are dominating compared to the inertial forces. So uh, this means that you can ignore force convections which are caused by those inertial forces, and you will have free convection in your system. Okay, so I hope this is clear. These definitions are extremely important, and you must make sure that you understand what these dimensionless groups mean, because they help us to identify what type of convection we have, and they also help us to find out what type of flow we have. So to see what type of flow we have, that means if the flow is laminar or turbulent, or if there is both, we define another dimensionless group called the Rayleigh number. Now Rayleigh number is a simple product of the Grashof and the Prandtl number. So if you remember, in chapter 6 we had defined the Prandtl number, and if you notice that we have a subscript of x here. Now what that means is that this Rayleigh number will be different as we move along the plate. So say we are moving along the plate, and as your x increases, your flow may transition. Your flow may initially be laminar, and then it may transition to a turbulent flow. So that's why Rayleigh number has a subscript of x, and it has uh, the viscous and thermal diffusivities in the denominator. And the transition limit for a vertical plate is usually 10 to the power 9. So if your flow, so for a vertical plate, if your Rayleigh number over the plate, so now notice that we have a subscripts of L. That means we are looking at the entire length of the plate. So across the entire length of the plate, if your Rayleigh number is between 10 to the power 4 and 10 to the power 9, that means you will just have a laminar flow created due to free convection. And if it's greater than 10 to the power 9, that means that your flow will be turbulent, and you will have to use your equations accordingly. Okay, so it's very important that we know how our flow is, because as we'll see uh, in our problems, or in some future lectures, that the equations that we use for heat to find the convection, or to find the heat transfer coefficient, depend on what type of flow it is. So your equation for heat transfer coefficients or heat transfer will be different for laminar, for turbulent, for a vertical plate, for horizontal plate, for internal flow, and for external flow. So that's why it's important that you know what these numbers are.